You all. Today, what we would like to discuss is uh, necessary theory for our today's demonstration of two, three programming paradigms, all come under the high throughput computing, as well as the some theory behind this actually. So, even though I have put the emerging trends, what I discussed today, it is combination of many things, and we should get idea about how the programming paradigms are really working on the cloud. Last time in our demonstration, we discussed about the high performance computing using Slum scheduler. That is the cyclic cloud computing. Now today we discuss high throughput computing, and we try our best to demonstrate some of the programs which we really use and what are the issues. So in today's lecture, at high level, it comes under the job scheduling resource management software. And if you go to the one or two levels at below, then the programming environment, Apache Hadoop and Apache Spark, and Oracle NoSQL, this Oracle Berkeley databases. And we also discuss use teletraffic data, how people are working on the cloud. These are the things we'll discuss today. So as you all know, I think we have spent enough time to understand the deployment of various cloud models, as well as the various delivery services and the infrastructure. The infrastructure, distributed infrastructure, resource virtualization, as well as the different kind of system resources and defining attributes. All these things, if you see, all the five will constitute the many aspects of the cloud computing. In that services, we have the privacy and security is there. In the resources, we have the software as a software services also very, very important. So these are the things which we know very well. And we already discussed earlier about high performance computing systems, where the clusters, where the each node in the cluster have the many devices and accelerators. Whereas high throughput computing, we have the peer-to-peer network, different kind of web services, and we have the virtualization, we have the Docker, and we have the containers, we have serverless computing, all things are there. Now we'll go a little bit ahead also. Generally, cloud infrastructure architecture looks like this, where you have the lowest, you have the many physical servers, which are completely virtualized, and you have the frameworks and workload management, and you have monitoring and management tools, and you have the different kind of virtual missions templates, virtual missions clusters, and we have the administrative workflows. We have various services portal. We have the private cloud as well as the public cloud, integration of both. And this is how the overall a simple way of understanding cloud architecture. And these are the three pictures where we talk about the large high performance computing clusters. These also come under the high throughput clusters. These are also used for the typical distributed AI training and machine learning and deep learning. Here, when we talk about the replica from the high throughput computing, we discussed that when you have master and slave architecture for the typical Hadoop MapReduce, you have Yarn as a scheduler, you have NAM node and data node, and you have job tracker and task tracker, where the replica on the same rack is available. The three replica copies are made, where one replica copy is in the same node, another replica is in the same rack, another replica is in different rack, All these things constitute the replica. And last time we discussed about the replica and resource management is the edge cloud infrastructure. Now we also discuss about the how Hadoop distributed file system and how Hadoop MapReduce and how the structured data sets using key value pair, unstructured data sets using NoSQL. All things have been discussed by many experts since last 5-6 days. Now we'll go a little bit about the programming side of these things also. So, and we also discussed that high performance computing and high throughput computing both can coexist in the job scheduling and resource management. That's where the Apache Hadoop Yarn resource scheduler, where you can integrate a POSIX compliant MPA parallel file system, the raster file system or the general file system with the Hadoop distributed file system HDFS. And this is how the picture really shows that the both you can run the simultaneously jobs on high performance computing as well as high throughput computing. You can have many applications where you require HPC resources as well as the high throughput computing resources. Today, most of the programming paradigm which we are using for the AI, ML, DL, they are all running with the PyTorch and distributed Spark Python, TensorFlow Python, and all integration is happening. That means under the cloud, the cluster, the complete cluster will have the HPC resource scheduling, job management software, as well as the high throughput computing, yarn schedule, everything is integrated. And these are all integrated with the popular Slum software, which we discussed, that we need to understand. And we also discussed about the how HDFS and how Lustre file system basically works on the high performance computing and high throughput computing, how both can coexist also when we really run jobs on the cloud. And both the file systems as well as the compute nodes, they have many kind of accelerators, everything. These all things we discussed. We also discussed about the how the Hadoop Yarn schedule has come, how HOD, Hadoop on demand architecture was there earlier, then how the Yarn resource schedule has been come out from the beginning, and these things now we'll see. We also looked into the various aspects of the various cloud platforms. One is Google, Microsoft, Amazon, and then we also plot where the Cloudera, and then we also discuss. In all these things, what is important is NoSQL database is growing in the last 10 years because of the huge heterogeneous databases which are existing in many companies, and all the companies, they access the cloud computing infrastructure. How do we integrate this NoSQL databases and provide the queries at faster thing? That means if you have a large NoSQL database, how do you process the search operation? How do you integrate multiple databases? These are all the issues in the database perspective. Whereas in the relational database, things are MySQL, Oracle, they are there from so long time, they are little bit easy actually. So we need to focus more on the NoSQL database, that we will see actually. And we also discuss about the edge cloud computing system, where we talk about the replica and resource management last time, and we are going further ahead in these things actually. Now what we do, first we discuss about the application perspective. From after completing application perspective, we look into the programming paradigms, and we also run some of the programs which we really managed to do actually. So now what is important in the application perspective is what are the data processing challenges, and what are the data staging, what are the data accessing, how the data storage, all these things are very, very important. We give one example. From this example, we also demonstrate some of the programs which are really required in this actually. So this is a typical telecom traffic application, where the you have the highly 5G telecom traffic application data. The data will come from the data extraction server of the telecom. Once the data extraction server data received, then you run optimization algorithm. The optimization algorithm running on the one high throughput computing or HPC system. These HPC systems, they're available on the cloud or they're available on the lab actually. When it is available on the cloud, it runs the highly optimization algorithm. It comes out with various paths to move the traffic from origin to destination. That means in this kind of application, the traffic comes continuously. Every 5 minutes, telecom traffic comes. The telecom traffic means there may be 100 cities, 200 cities, or 1,000 cities. They keep communicating to different cities. That is called OD pair, origin and destination pair. How many origin and destination pairs are there? How much is the communication? How much is the edges? All the things we need to understand. Here, the entire traffic data is processed on the big supercomputing system. That's called high performance computing system. The high performance computing system runs optimization algorithms. Optimization algorithm gives max flow, min cost, that is minimization of cost, maximization of flow from origin to destination. What are the parts, everything, all the things we need to do it actually. So it is highly compute intensive, highly data intensive actually. Let us go more detail in this also, you'll understand more. So from the hardware perspective, if you really see, you have the core switches, you have the edge routers, and you have the different kind of traffic data comes, and data we are getting through the different kind of telecom network, and the data goes to the supercomputing. Supercomputer consists of high throughput and high performance. Then you do the analysis. So what you really see is that how many core routers, how they are connected, how many edge routers, how they are connected, how many access switches are there. All these things you may really see in the actual real life scenario. You may have more than a few lakh kind of router devices, everything that we need to process the data actually. So this is also from hardware perspective. So what really happens if you really look into the overall this kind of application is the telecom data is received from the telecom stations where you have the data comes to the routers and switches. All the data comes to data extraction server. Data extraction server models the problem as a graph, and the graph model is given to the supercomputer with the what is the cost and capacity of the telecom links, that is origin to destination pair. What is the demand which we have to go through? So that means we need to find max flow, min cost that runs on the supercomputer. When you are running on supercomputer, the supercomputer will have the GPU sector, will have the CPU sector, will have EPC accelerators. All these things basically audio, video, text, we need to process it. Once you process it, again it goes to the network control, that is data extraction server. The data extraction server gets the output and checks how it is the optimal path from origin to destination, and it will control the entire network. So this entire process is basically done on a HPC supercomputer with highly integrated current implementation framework. That is very, very important. This is one of the project. Now, if you go more detail in this project, if you see on the extreme left of, you extract the traffic from the live telecom network. Means we sometimes very difficult to get the live telecom data because of the privacy and security. So we look into the already data at the metadata at the switch at the router level. Then we get the data. Then once we get the data, we need to model as a graph. Here the data is stored in Berkeley DB. Berkeley DB is a NoSQL which we discussed also. Now data stored as a graph. The graph consists of set of OD pairs. And then every OD pair, they have a cost and capacity, and there is a demand also. So cost, capacity, demand, and you run the traffic, then you get the complete model, then you get the traffic matrix. That's what the second block, we construct the traffic matrix actually. This traffic matrix and network topology, that is how the network has been laid on L1 core switches, routers, and edge routers, everything we configured. Then we get the network topology. Then we use the traffic matrix. Then we solve on the third step on the supercomputer LP solver. This LP solver is basically linear programming solver, where they have some open source software and they have the commercial software they solve. When they solve, what we solve is that how many number of OD pairs are there, how many number of edges in the entire network. and how many number of variables we are solving. Normally in real life, real situation, you solve 10 million, 20 million, 100 million kind of variables. What you see is that you can see few million variables can be solved for a small number of cities of 20, 25 cities actually. Once you solve this linear programming solver, we get an optimal path with the optimal path for the current set of demands. These current set of demands keep changing for every 5 minutes. Traffic also changes. The last one is that fourth one is these optimal paths again is given to data extraction server. The data extraction server now control the complete telecom network and make suitable changes so that overall traffic pattern traffic is controlled actually. So this position number 1, 2, 3, 4, where is the cloud computing will come into picture. One is how to store the large amount of graph data which come to the extraction server, that is storage in Berkeley. Second thing is that how to store the traffic matrix, which is a very dense or sparse. If it is a sparse, we need to use some compressed sparse format in store. And third one is that what is the LP solver input, what is the LP solver output, how do we store it? And fourth one is that what are the changes we do in the real-time network. So these four. All these four will happen for every time step of 5 minutes and 10 minutes. Then we need to process this data. So that's what the Berkeley DB storage is coming into picture. If you really see overall network, this is how the you can see the processing teletraffic. There are 4 stages. Every stage, large amount of data will come. That means what? Stage 1 at time frame. At what time we take the snapshot, and when we increase the time by every 5 minutes, if we take the time stamp as every 5 minutes or every half an hour. Let us take every half an hour. If we take every half an hour per day, we have 48 time intervals. Every time interval, we get the telecom traffic data at the routers or switches, and then we model as a graph, and then we obtain the traffic matrix, get the optimal routing path by solution on the supercomputer, then real configuration network control will do. So all these things, various level data is stored, the data is put up in the Berkeley DB, and when we solve the same problem for every half an hour, you get the data changes, then overall the data will be in the gigabytes to process the telecom application. A simple example is here you have the to make ease of understanding, we have a simple graph of around 20 cities, and we have taken every half an hour, we need to get the snapshot of the complete telecom traffic, and we divide into the total number of intervals will be 48. So now minute by minute level actually done at the real time, but we are not doing here for simplicity's sake, we take half an hour. So this is how the 20 cities means every city communicating to any other cities. There are 19 cities are there. So totally 380 OD pairs are there. 380 OD pairs, they are not in communication. Now let us see how much data we generate. Then how do we solve it? We'll see when we do the thing. How do we really do this kind of graph modeling? There are various models are there. One model is that telecom map model, where the telecom data represented as a graph, where the number of phone calls depend upon the affinity of the place and the activity of the place and time zone and mapping actually. By looking into all this affinity, activity, time zone map, we can get the total number of phone calls going from origin to destination at various time interval. Once you know the total number of phone calls, we can convert the phone calls into voice over IP, and then we see how much is the how much size of the data going from origin to destination. So this is what you see in the picture is various links which are there to telecom between the two cities and various paths where the message will travel actually. Okay. Now in all these things, what we have seen, for example, I just come here. The activity happens midnight 0 to morning 4 o'clock. If you see the number of phone calls going from one city to other city, I gave some activity factor as a 0.6. 0.6 means if the population is about 10 million, and if I choose the 0.166, that means overall 10% is in the 10% of the city population is in communication. That means 10% of the city population is going to many many places in the many cities in the India actually. Now morning 4 to 8 it is 0.48, morning 8 to 10, morning 10 to afternoon noon, afternoon noon 12 o'clock to 2 o'clock, and even again afternoon 2 o'clock to 6 o'clock. It's a peak. Peak means almost not 30% or 40% of the each city population is in the telecom network, and they are sending the a lot of they are exchanging the voice or IP or the WhatsApp messages or the SMS or making phone calls. All the data we can get the metadata information at the switches or the routers actually. And what we use, how do we get this data? How do we store the data? We use Berkeley DB. That is also very important, which we'll discuss some of the programs which we run also. Now what we do, we'll go back again. So this is what there. Now that means when the traffic, you have to extract the traffic from the network, and the traffic, once you get the traffic, we get the number of OD pairs, cost, capacity, demand, that we show in Berkeley DB. Then we build the traffic matrix, that is also stored in Berkeley DB. Then we get the intermediate input output, that is how to solve optimal routing algorithm using LP solver. The last one is how to reconfigure the network using the output of the optimization algorithm. At each stage, you get some data to store, and then each stage may be half an hour or 5 minutes. You take the snapshot. That means this data comes per day, data comes for a week, data comes for a month, and data comes for a quarter. And how do we store it? So that's the use data in the telecom 5G telecom traffic, which goes more than 10 GB, 100 GB kind of data. So now when we store using the Berkeley DB, how do we address these things? That also we will discuss actually. When we discuss this aspect in the Berkeley DB, normally we also know what is the graph size, what is the cost capacity, what is the demand, how many commodity pairs, and how do you store the traffic matrix, dense or sparse, and what is the optimal routing algorithm, and how do you put all these things in Berkeley DB is very, very important. If you're able to put in Berkeley DB for one time interval, you have 48 time intervals per day, and then you have the 7 days per week, and you have 4 weeks per month. And how do you really store this data is important actually. Now what you see is that for synthetic data using, we calculate the number of packets and bytes per second. City 1 to city 2, you can take 5 cities as a metro cities, or remaining you can take many cities, and then you try to estimate number of phone calls. Number of phone calls is calculated by taking the mathematical model. Mathematical model means affinity as a mapping, as a time zone and activity, and then population, everything we consider and make number of phone calls. These number of phone calls may vary from every 10 minutes also. Peak number of phone calls is from morning 8 o'clock to afternoon 4 o'clock, peak number of phone calls. Every phone call, we measure how many bytes of data you are moving, somewhere near 200 bytes. And then we get the total number of bytes which are going through the network. Then we get the complete traffic actually. So the entire traffic, how do we process? We need a system in the cloud. And how do you storage? We need a storage in the cloud. And how do you do the AI analysis? We need a storage in the cloud. When you do AI analysis, it becomes high throughput computing. When you do the linear programming solution, it becomes high performance computing. And when you want to do the AI analysis, we need to access the data for the last 1 day, last 2 days. Then we need the high level programming APIs and how to store it. So these are all well mixed problems which are there in the high performance computing, high throughput computing for 5G teletraffic application. What you really see in this picture is that how many number of phone calls going from one origin to one destination. And what are the number of phone calls means? Basically is morning, you divide into the morning midnight 12 o'clock to morning 4 o'clock, morning 4 o'clock to 6 o'clock, morning 6 o'clock to 8 o'clock. You divide into the time zones, and then you start communicate. You start synthetically generate the telegram traffic. Then you come to know how much is the GB available, how much GB of the traffic goes from one origin to destination, how many paths it has to travel, which you see from this given picture also. For example, if you take Mumbai and New Delhi, Mumbai is sending 141 GB, whereas New Delhi is 204 GB. That means from New Delhi, inflow, outflow, everything we need to calculate. It is mainly going the outflow, that is coming, going out from the New Delhi to every other city, certainly Mumbai to every other city. So this is how we can calculate the traffic also. Now we store the traffic matrix. This entire traffic matrix, if you really store, it becomes in the more than GBs actually. That means morning 4 to 8 o'clock, your total traffic is going more than TB, 1.5 TB. If you do the morning 8 to 8:10, 8:10 to 8:20, 8:20 to 8:30, the total size of the data goes more than terabytes. And terabytes of data goes in the entire network. We need to find the optimal routing paths and we need to control the network. And how do we store this data in the cloud is a big issue. What you see in this picture is that all the 20 cities which we have taken, where one city is communicating to 19 cities, we choose some interval. In that interval, what is the basically amount of traffic, everything. So if you really look into this thing, the amount of traffic which you measure, and then in the GB, and then how do you, so there are two issues. Some amount of data is in the buffer. Some amount of data you are processing. Some amount of data will come from the telecom. That means three types of data which you are processing. One data you need to store in the cloud. Another data you need to run on high performance computing or high throughput computing. Another data for AI analysis you run on high throughput computing. So now this data, what you see is morning 4 to morning 8, we assume 15% of the every city population is in the telecom network, that is they are involved in the communication. Then you really see overall the size of the data which grows actually. The question is, what programming paradigm do we use? What we can really run this program, that is also issue. And we can also generate such data, live telecom network data as its own security, privacy, and customers will not share. However, we can generate synthetic data using graph-based algorithm. The graph-based algorithms are very, very popular. One is Erdos-Renai algorithm, scale-free network, small world network. All these algorithms we use it, generate the large amount of graph data, which is very close to the real-time telecom traffic actually. How do you process this data and how do you store the data? For all these things to store the data, we have the different kind of storages are there, Neo4j and Oracle NoSQL, all the storages are there. They use different kind of database approach that we'll discuss also. Now, the entire crux is that how accurately construct the traffic matrix. The traffic matrix basically it is traffic using the traffic matrix as well as the network topology. We run the optimization near programming algorithm that gives optimal routing paths from origin to destination, that is minimize the cost, maximize the flow. So now the question is how the network topologies really handle these heavy loads and what are the congestion, everything. These all things we need to address actually. That means huge amount of computing goes on the high performance computing, HPC system in the cloud, high throughput computing in the cloud. That means when you get this data in first 1 hour, second 1 hour, third 1 hour, data keeps increases, then you require more and more resources. Then the cloud with elasticity will able to solve this kind of problems actually. Now what you really see is that a typical telecom network data where we have done visualization. What we see extreme below is a RailTel network where the MPLS network is there. You have the blue color routers and switches, they have 10 Gbps. Red color, they have maybe 100 Gbps. And from blue color to output, there is edge router, they have maybe 5 Gbps or 1 Gbps. This is how the actual network is there. What you see extreme left is that another European network actually. What you see on the extreme top is also European network. So these are the German network, European telecom network, huge amount of data traffic it generates. What you see in the middle is 5 metro cities, Mumbai, Delhi, and then Hyderabad, Bangalore, Chennai, Calcutta. All these 5, if we really develop synthetic data, how the real traffic look like. So this is what the better way of understanding this data actually. Then what we do, today we will to run this kind of huge amount of data, we need to solve using some programming paradigms. First, we do the standard Hadoop MapReduce programming paradigm, where what is meant by MapReduce program model and how do we solve this program. Then we will discuss first in the overview about the MapReduce, and we'll run the application. So here, it's a basically Hadoop MapReduce is one of the parallel distributed computing paradigms. Many of them must have discussed. I give you simple overview. Map initially the entire data is converted into record pairs and distributed to the compute nodes using HDFS. Using HDFS, the data is partitioned into chunks. Every chunk is 128 MB, and then it will be distributed onto all the nodes of the Hadoop cluster. Then you define two functions. One is map function, other one is a reduce function. The map function reads a key value pair, applies to user specific code, and produces the results called intermediate results. Intermediate results are aggregated by reduce, another specific code gives a final output. So in brief, you write two functions, one and map function, reduce function, and this is how it happens actually. So this, if you really elaborate a little bit, let us see. So what is the first step is basically we'll see. Then we run simple programs also on our system. Input map reduce function is organized in records as per the input specification that will yield key value pairs, each of which is a K1 V1. In the case of telecom traffic analysis, key and value. Key is the city, value is the how much time it takes to send a message from time takes to message goes from origin to destination. Key is the cost, capacity, and demand also. Value is the time taken to reach actually. Like this, you can define key value differently for different applications. The way you define the key value, the way you define the map function is the most important actually. So now that means once a given input data is distributed into the chunks on the every node using HDFS, each chunk size is 64 MB or 128 MB, then map function will the map function applied to all input records. Input records are stored in the many systems, and many map functions will go there and execute one by one for each record. It generates the intermediate data, which may be 0 or more actually. The intermediate data is another key value for records. That is also stored in the memory or may not be stored in the memory if the data is very used. Then all the intermediate values, that is K2, V2, are collected and reorganized so that records with the same key. That means all the records which are there in every node, and then you collect them and reorganize with the same key and put together in K2 and the list also. So this is what the intermediate data, that is what the mapper, reducer, combiner, sorting, shuffling, many things will happen, which I will not discuss in this presentation, but you must have idea. Then after completion of this one, the reduce function, the user-defined reduce function is called once for each distance key, and then find out the output and so produce the results actually. So that means the final output is basically done by the reduce actually. It adds all the listing or and then gets the final result. So what is important actually? All the key value pairs after combining is done collapse into the final result. So that means independent of the storage, the MapReduce programming model basically handles all the things actually. So MapReduce reads the key value pairs from the underlying storage system to reader. Now I will execute some codes here. See, this is what the typical Hadoop MapReduce file splitting, and the input data is there and splitting has been done. Then map function executed. That is, it's basically word count. It basically each word and number of appearances, occurrence of each word. A appeared twice, C appeared one, and CBD appeared 111. Then you do the shuffling, you organize all the data, then you call the reduce. That's how the happens in the typical MapReduce. From the programming point of view, what we do, we'll try to see the programming point of view here actually. Let me go to the system here. So I have one system here. You're able to see now? System? Are you able to see?
No, sir. We are seeing only slide.
Okay, okay. I just wait. Give me a few minutes. I'll set up the system and get back.
Okay, sir. Okay. Okay.
Share. I'm sharing the screen. Is okay now?
No, sir. We are only able to see the slide.
I'm just checking this. First, I had to stop. No? Are you able to see now or no?
Sir, we are on the slide basics of map and reduce. Same one.
Ah. Just few minutes. I'm setting up the system. Few minutes.
Okay, sir.
So what I would like to discuss now is more about the how we really run the Hadoop codes, what environment we have set up, everything, and how the large amount of data can be processed that I wanted to demonstrate actually through some examples. And then we'll see. Just wait for a few minutes. I'll be back after 1 or 2 minutes. Let me complete this basics of the map and reduce. Then we have the Spark also there. Then we also have the Berkeley DB. First, we run the Hadoop map reduce some codes on our servers. And then we get back to the Spark. Then we will go to the Berkeley DB. So there is some issue with the accessing the server. I'm able to access, but I'm not able to get the display. I think maybe in few minutes we'll be able to do.
Okay, sir.
you able to see now?
Yes, sir.
So what you see, I have one, this system is under the cloud with the yarn scheduling running actually. What this system does basically here, earlier generation of Hadoop MapReduce is Java and then integration with Hadoop MapReduce HDFS. Now we have set up the Hadoop MapReduce with the Python actually. So now in this Python kind of framework, let us see how we are able to compile these programs and everything actually. First we go to the some of the directories which we have in this actually. So we have the typical Hadoop Python environment. So we have installed.
Sir, you have muted yourself.
I have the administrator called Hadoop.
Sir, you are not audible. Sir, you have muted yourself.
Now okay, no?
Yes, sir.
So now the normally what happens, this particular environment setting up everything, it is taken care of when you really run on the cloud. In that there is a many of the features are there where you distribute file system and then all the demands has to work, and then there is a yarn and stop all and start all actually. So that means you start all the services of the Hadoop. This is by default taken by the cloud when you really run this application. When the cloud provides the Hadoop high throughput computing, Hadoop distribute, Hadoop MapReduce programming environment. Let us start all the demos here. Start all. So that this means start -all that means all the demands and all the services have to be activated. So that we are doing first step. So now it is doing actually, it also gives the a lot of environment and everything. Here we are running the complete Hadoop on single node. Now we can run on the same thing with a different kind of configuration on the multiple nodes. As you all know very well that many speakers have conveyed about the Hadoop MapReduce master slave architecture, name node, data node, job tracker, task tracker, and all these things are basically now services, everything is node managers, all things have been done now. So that means here now Hadoop environment is fully set here now. Now we go to the one of our simple program. We do the different, first we go to the input file, cd input file. So this input file is more input dot text, some text is there. I'm doing some word count, and this is what the input text file is there actually. So pushing onto the Hadoop distributed file system, arranging it to chunks, everything is done internally. Now, this particular file, if you see, it is more than 336, nearly more than 1 MB, more than 1 MB it is there actually, 1.2 MB is there, more than 1 MB. So what I do, I take the small data and run it, and I also change the inputs also. I go to the other inputs. Here we have seen what is the inputs. There are three inputs are there. One input is 8K bytes, other input is maybe 0.6 MB, other one is 1.2 MB. So that means when you traditionally run this word count application in normal programming pattern, not possible. Whereas this kind of data comes from the telecom traffics, or it comes from the typical graph theory computations, all these things also there. Now let me just copy this small input that 1.txt to the actual input. Let me see input. So I copied using one command. It is done. Now I go to the input, CD input. Are you able to see now? So
Yes, sir.
input is
It is yes, it is visible.
visible. So this is basically 8K bytes actually. Now I will go to the program. Here I have the, I use the on Makefile. The Makefile is a utility where you can compile the program, execute the program and do. The Makefile calls run.sh is a script I'm using. Almost all, we use all kind of scripts to run the applications because you have Hadoop Python environment and you have Spark Python environment. You have Berkeley DB Hadoop environment. So many environments are there. All environments we need to remember. That's why we use a scripting file run.sh. Let us see what the script file does. That is what run.sh. This is how the run does. The script file will ensure that all the input data is copied onto HDFS and partitioned into 128 MB, 64 MB, distributed into all the nodes. All the things have been specified here in this program. If you really see more run.sh, who have my example name, word count Python, and copy word count input into the local to HDFS, and then HDFS, he put the file and all the other environment of the word count, job, jar, and then Hadoop tools and everything, Hadoop streaming, jar, all things have been integrated with Hadoop Python. Then ultimately you get the output back to the home directory. This is how the things have been done in the run.sh script actually. So these scripts will be there. Then you have the typical mapper.py. This is how the map function is the map function. How do you write the map function? Is we use a line split and then occurrence of each word and number of appearances, and then we get the intermediate data. Is mapper.py very easy to understand. I'm not going more detail about the mapper.py. This is about the reducer also. Reducer is the basically it for every word it gets the count and then get the final result also. So the advantage of the writing program in the mapper and reduce function in Python is it's more compact, easy to understand, and easy to write also. And then now we will compare and execute the program also. Let us see what it does actually. So we say make. Make is the command to run the make file. So now it is running run.sh. After doing run.sh, it will see, it will go through the many things. So now it is talking about map. Here we talk about Yarn client submitted application. That means resource management and job scheduler. Yarn is running on the Hadoop cluster. It submits the jobs, everything. You have the MapReduce job running, number of mappers, number of reducers. It talks about everything. Now here, how much is virtual memory and how much is the you use it? All things will also explain. This is how the word count happens. So now if you see the CD output, you get the output as the you get the output also here, all the occurrences, everything. Now if you're able to see here this one, now what we have to do is we will go to the input, CD input, and we see the input is 8 KB we are given, only 8 KB we are given. Now we go back again, we say make clean, it cleans all the data, everything, complete. Now it's completely clean now. Now we go to the other inputs and we now will see what are the inputs available. We will run the another program with 648 more than 336 0.6 MB, 0.6 MB data. Earlier we take 8K bytes, now we take 0.6 MB. So that means first we need to copy this input, copy input SCP input 2.txt dot slash double dot input slash input dot txt. So it is done. Now you go back and input and check. CD input ls-l, it shows that now 0.6 MB data is considered as the input actually. Now again, we go to the same Hadoop Python examples. I'm using Ubuntu OS for my running job on one of the node of our cluster, and we are not running a full cluster because very difficult to get the Hadoop cluster operating for a kind of lab. Now I do make clean. I'm cleaning everything. Then I will see ls-l dot slash input input.txt. So this is now 0.6 MB. So now I will do the make. That means I'm now running the program with 0.6 MB. Earlier I have run the program with 8K MB. Now you can see that means the amount of telecom data which it comes for every 5 minutes, 10 minutes, we need to process in much faster. For that, the large amount of data, how it is processed, how the data has been copied onto the every compute node using HDFS, where the chunk size is 64 MB or 128 MB. Here you see the yarn scheduler, yarn client, map reduce, everything. I also display this output. What I am understanding from the output also will tell you in the one of our presentations actually. So now here, now because data is more, it is basically able to do the work actually. Now if you really see the input differently, the input is also very high actually. Large amount of input is there. So now the data is more than 0.6 MB. So now work completed actually. Now if you really see again CD output, ls-l star, this output is more than the count, everything, words, everything is given actually. So now that means this is how we can able to do the Hadoop with the Python environment. Now we can do same thing with the Spark Python. Then we do the Berkeley DB also. So now we do the make clean as usual. So we are cleaning. So what we have done here is basically what is the output meaning. We'll understand what is the output when we look back to the presentation. Now I'll temporarily come back to the system now. I'm just share. This one, share. This content. You're able to see now?
Yes, sir, we can see the slide.
Now what we have done is Hadoop Python code. Let us see what output has come and what we need, what we have done to get idea actually. But nowadays, these all things done on the cloud automatically. We don't have to much bother, but we should know. These are the scripts which invoke all the services. We have run start all.sh and then remaining all automatically. When you run all.sh, all the services are basically activated. Then we can also have the stop all the services also. We can stop the name node, data node, secondary node. So these all things we can do. Stop all services demos actually. So we use Hadoop G login ID for this. Now once we complete all these things actually, then when the program runs, the script file internally it copies the data from the local to HDFS, local HDFS, when the copy basically indirectly it says that the entire data is partitioned onto the chunk. Each chunk is 64 MB or 128 MB. Okay, that has been done. Now this is what the all the line numbers in the script file which I have run. Each one talks about the how to copy the input.txt, the input.txt into the HDFS, and all the arrangement of records, everything is taken care. Then is how the script file, all the Hadoop libraries, Python libraries, and then you have the mapper and reducer, everything has been set also. After that output, once it runs, after the output, basically how to use the output, everything. So you get lot of data on the screen. That also very, very important. So that's what the, this is what the source code. This is what the mapper code and reducer code. This is all the way we write these codes in the Python, which is very easy. Earlier it is written in the Java. Now it is, now let us see output. When output basically we have the program is running and then we have the outputs are there. It also talks about the, so what we have done, all these things we need to understand the complete framework in the scripting file also. This is one of the important thing. Now let's see, when you compile the thing, adding word count clause, reducer class, mapper class, and then copying onto the HDFS, then automatically you get a message input text file to HDFS, run the job in Hadoop, copy the output file to HDFS, write the terminal output. Now, when we do all the things, how the name node, data node, and then yeah, Hadoop yarn, and then job submitter, map reduce, input file, all data comes on the screen. We need to understand this data, how the job is basically running actually. So what you really see is that configuration details, map reduce job, number, everything, running job, then the successful execution, number of mappers, number of reducers, everything. Now here, number of bytes read from HDFS, number of bytes write. In Hadoop MapReduce, read more, write less actually. That's where these all operations you come to know. Number of bytes read, number of bytes written, read operations. Then also map task, reduce task, and then how much time taken for the map task, how much time taken for the reduce, number of map tasks. All these things are basically done. Then map input records and reduce input groups, combine input records. All this data you get in the output file that we need to study. Once you study, we'll understand how much data we consider, how the HDFS distributed data onto the various nodes, what is the chunk size, 64 MB or 128 MB, everything we come to know actually. Then also what is the physical memory of the every system, what is the virtual memory. Why? Because virtual memory, physical memory, most of the Hadoop MapReduce, when we do the mapper task, when you generate intermediate data, originally input data is uh, is input data meets the memory requirement or not. If input data is not stored in the memory, it goes to the storage. That means the input data is in the memory, not in the memory. That means physical memory, virtual memory, peak physical memory, reduce, all things we need to understand also. So that's what input. Whenever we process Hadoop MapReduce program using Python or Java, first is the input data, when it is partitioned onto the every chunk, does it fit into the memory or not? If it is not fit into the memory, it go to the storage. All this information we need to understand completely. So this is how the MapReduce framework totally muscle memory. So now ultimately you get the output actually. So now I will just go to my presentation and talk about the Spark also in this context. One second. Yes. Where is this? Demonstrate this third one. Visible now?
Yes, sir, it is visible.
So what we have gone, we were talking about the MapReduce application framework. Then we have gone to the laboratory session where how the Hadoop MapReduce with Python, where we have run one simple MapReduce application. Similarly, we can run many applications. In the MapReduce application, we have taken one input of 8K bytes. Second one is the 6 MB, 0.6 MB. Third one is 1.2 MB. Now 1.2 MB or 0.8 MB, if you really want to solve using traditional methods on high-performance computing system that has POSIX thread formulation of threading model or the OpenMP high-level threading, it really becomes difficult to accommodate this kind of huge amount of data. Similarly, if you want to run MPI, how long is the file, how many lines are there, distribute the lines on every processes by using MPI, gather, scatter, and do. Whereas Hadoop MapReduce, there are some advantages because data is very, very huge. So now we'll go much details in this. What we have done is map written by user, and the second one is reduce written by the user. These two written, not all applications we can write map and reduce function. We need to carefully see which applications we can do this map, reduce, and Python. In the case of telecom traffic application, large amount of telecom data is stored. That is every person. What is the demand, where he wants to send the message, where he wants to reach the call. That means basically key is the origin and destination and demand, and value is the shortest path from origin to destination. So if you're able to do such kind of thing, then you can able to accommodate 5G telecom data on the cloud easily using Hadoop throughput computing, and that's what the Hadoop MapReduce. Now let us see a reduce function. Limitations we told, many problems are not easily described as a MapReduce. Only disk typically slower than in memory. So normally, alternatively is that if you have large memory, then you can use the Apache Spark. That also we will discuss a little bit and go back to the some programs on Apache Spark also. So what is Spark? That means when you have systems with a huge memory in the cloud, then you can ask for the Spark programming environment. When you have the huge memory in the huge memory systems in the cloud, that's what we call ICE. More some of the clusters head node have more memory, remaining nodes have the less memory. Those nodes which have more memory in the cloud, then if the Spark runs there, then you run on the Spark rather than on the cluster. The advantage is cost of renting the nodes as well as the processing power is very high on the large shared memory actually. So that means there is a Hadoop MapReduce Spark. Now they have developed the Hadoop MapReduce Python is one with earlier Hadoop MapReduce Java. Now Hadoop MapReduce Python replaced by the Apache Spark Python. Apache Spark Python also we should know. So what is the advantage of the Apache Spark, we'll tell you. And we run some of the programs also in Apache Spark. Then we go to the Berkeley DB. So efficiency, all the data which you are storing, which you are processing in application can be called as the graphs, and then you have large amount of in memory. Because of in memory is there, it's a faster in memory actually. And usability, there are the rich APIs are there, Python APIs also there, less code also. So now in the Hadoop Apache open source component, Apache Hadoop is one. There they have the many things are there. Then Apache Kafka is also one, very good for distributed telecom data processing. That's very popularly used. Yarn is a scheduler which is integrated with the cloud schedulers. And Spark, which we are talking, remaining all, we are not going more details and everything. Let us see. What is the Spark? A Spark, a driver program that runs on the user main function and executes various parallel operations in the cluster. That means your then what is the abstraction in the kind of Spark? How the input data is partitioned onto the various nodes and stored there. where each partition is a 128 MB chunk in the Hadoop. Now in the Spark, what they do, they use concept called RDD. RDD is Resilient Distributed Dataset RDD, which is a collection of elements partitioned across the nodes of cluster that can be operating. That means just like how Hadoop distributed file system works, similarly RDD works. In the last 3-4 years versions of the Spark, there is no need of HDFS. Spark runs without HDFS completely. That means RDD handles many things. Why? Because large amount of memory is there in your system, then you can process the large data actually. So that means how to construct the RDD and how do you reuse many parallel operations, and if there is a node failure, how the RDD can recover from the node failures. All these things are very important. And second abstraction, one abstraction is I told you about the RDD. That's what the first abstraction. Second abstraction is shared variable. The abstraction is more important when you solve large data intensive problems in the cloud computing. Now, last time we talked about MPA and Scrum scheduler. And today we are talking about the Yarn scheduler and Hadoop MapReduce and Spark Python. All these things are basically nothing but different kind of job scheduling and load management, resource management software caters to the need of applications. So what is second abstraction? Second abstraction is it also has the parallel operation. Parallel operation means broadcasting variables, accumulating the added results. All these things are how the variable to be shared across the many tasks. All these things are provided in the Spark. It makes the Spark runs parallel, function runs in parallel different nodes also. Let us see this thing. Now, to do this program, we have to put import org apache.spark, Spark context, import org apache spark.spark conference, and Spark program, how to create the Spark context object, and how to access the Spark cluster, and what kind of application we are doing. All these things are also completely bundled as the APIs in high level, so very easy to write Spark programs with Python. Earlier, Spark with another programming paradigm is there, but now Spark Python is very, very easy, which we'll see also. Now, how to create RDDs and how do you parallelize existing collection, that is issue. And then all these things are basically, initially it was integrated with HDFS. Now slowly it has been moved out. Now there is no need of HDFS. Now let us see what is the RDD. RDD created by starting the file in Hadoop file system. Parallel operations already can be done. There are shared variables, accumulators also there, and the data can be shared across many parallel operations. These are the features which are there. So what are the other advantage actually? RDD expresses many things in a computing system where not limited to MapReduce. It facilitates more system memory, and it doesn't have to write the data to the disk, saving more time. And it is compatible with the Hadoop actually. So a lot of changes are keeping happening in the Spark. Now Spark is more popular actually. How the Spark handles the collection of records, how it spreads on the cluster, how the data set in the memory, whether it is caching or different storage, can we fall back if the minimum storage is not there, if the memory is not there, fall back to disk. All these things are extensions which are there actually. So now what we do, I will run some programs here. speak, no problem. You're able to see now?
Yes, sir, it is visible.
So now we have gone to another system where the Spark cluster is there. One node we have got access actually. See, here there are two things. One is first I logged in as a one login ID. Who am I? The CDAC login ID. So here I set up with the Berkeley DB as well as the Spark both. First, let me see. I need to set up the Spark environment. One important thing is Spark, Hadoop Spark environment, Hadoop Python environment. If they both coexist on one cluster means we need different kind of complex splitting where the Hadoop runs with the Hadoop G administrator, Hadoop administrator login ID, and then Spark runs in a different context. So we cannot have both the things on a single node, but we have on different clusters. Again, all this Spark environment and Hadoop Python environment, single user mode, multi-user mode, and running on a single server or multiple servers, we need to think all these things. So let me see. First, I have to set up the environment, activate the environment. I'm using Anaconda 3 here. So that means basically source tilde / Anaconda 3 /bin /activate. So this means you are activating a Spark environment on the system. Normally, when you do on the cloud, it automatically takes care of these things by the cloud when you so these are all. Now, when you do this activate, before activate, you get a login ID, CDAC, and Ubuntu. When you activate, you get a base, and then base is the source that it is activation has been done actually. Okay. So now we'll go to this one. We go to the PySpark examples. We have gone to the PySpark examples. Now we have the is visible now? Is it visible? Screen visible now? Hello?
Yes, sir, screen is visible.
So here we have gone to the word count, and we also have another example of the databases. We also have another example of typical scientific computing. We'll discuss these things in our presentation, and we also show some results also. So now I'm basically gone to the README. I basically set up the, first I have to clean all the things. That's why I use make clean. Make is a utility which we call make file here. And then you simply type normally we store as a make file as M uppercase, AKE lowercase. First I do make clean. I'm doing all the clean. Make clean is done. Then we directly so now we are done. We are compiling and executing make. Again, it is compared to the Hadoop Python. It has also showed the same thing, but it also written many things. Let us see all these things. Can we read to this one? Was it now? Now we can see we have run the program simply by making an output is there. CD output. Now we got the CD word count output. We got the output here, part this one. So ls-l part, this was the thing. And then you get the output as a part, you see output has come. Now let us go back to the input files here. CD input. Here I have input.txt, ls-l input.txt. That means it is a input file is I have taken a very used one 0.6 MB input file here. 0.6 MB input file ls-l input.txt is a 0.6 MB. Now I go to the other input what I have. I have another input. Let us run a bigger problem. Another input is 1.2 MB. 1.2 MB input is there. That we will write it actually. That means SCP input dot 3.txt dot slash double dot input dot txt. That means I am overwriting the existing input by 1.2 MB input actually. So it is done. Now we'll go back to again ls-l input dot txt. So this is showing 1.2 MB data. So now we run it. First we need to do the make clean. Make clean we are done. And then make we are running. So when you run now, let us see. The program takes time. Here again, yarn everything is there. Now let us see output file. CD word count output ls. Now we'll put for our thing date ls-l is exactly 522 output created. The output is part actually you can see. So what we have done here is now let us see the programming side. How easy is programming is more word count dot. I'm using only one program word count py. The Python way of writing Spark contest creation and Python program and split lines into word and counting everything. All these things are nothing but it's a more Spark Python is a compact version of only 15-20 lines. Whereas the Hadoop Python is more lines, Hadoop Java is much more actually. So that means when you have a high-end system on the cloud, high-end system is more number of cores, more memory on one node of the cloud, then you run on the Spark program. Now Python Spark GPU, everything is integrated. That means GPU, NVIDIA CUDA programming, GPU, AMD OpenCL programming, and Spark and Python. All these are nothing but today stitching many languages together to run your application. So that means here if you see this program, what you have is the import Spark session builder, and then Spark contest. Then you read the text file, then you get the words, mapping words and reduce, everything is done very fast. So what does it mean? Map is the one API library call. Reduce by key is one API library call. And flat map actually. That means three programming APIs, I use it to run the Spark program. Whereas in the case of Hadoop Python, I write separate mapper and reducer. In the case of Java, I write much more lengthy programming. So there are some advantages in this kind of thing. So we tried with the 2-3 different inputs. Now we'll go to the again word count, and we have to do a make clean. So make clean has been done. Then again we go to matrix vector input. Here I'm running matrix into vector. Matrix into vector is used in almost all the financial applications, all the database industry applications where the extract some information from the data and multiply with the vector. This is how properly use the matrix vector multiplication. In the case of AI algorithm, they use matrix grouped matrix into matrix multiplication algorithms. So let us see how lengthy this program also. First, as usual, make clean. I have done make clean and more matvec.py. So here the example matrix is 4x4 I have shown, and the matrix is stored in a row index, column index value, typical to the what we store in the matrix A, matrix B in the Hadoop MapReduce Java or Hadoop MapReduce Python, where the records row index, column index value. To store this data in a record is very easy actually. That means when you write actually programs, you can give a key as the row and column value is the value which is there actually. In the vector also we stored like this only. Vector also given. So now all this input data commented. I have the Spark has got parallel operation, matrix underscore RDD parallel, vector underscore RDD parallel, that is automatically distributed, and vector dict, that is what the matrix multiply matrix into vector, that is also one operational matrix underscore RDD dot map. So now sum by thing, that's what the sum. So that means it's mainly consists of 5 programming APIs which you use in the matrix vector, which is also very easy. Whereas in the case of MapReduce, you define the key as one value of matrix, and then one value of the vector, you get the output as the A00 into B0. Then again, another mapper A01 into B1 and A02 into B0. That means you require n square mappers. Then you get the partial thing. So it's very long program, whereas here it is very easy. So let us see. I have done make and I have compiled. Is Spark submit matvec.multiply. This code is running now and then running the task. Everything is completed. So here, what I have done is I used one command call in the. I use the Spark submit. Spark submit I use actually. I use a Spark submit command and I'm able to compile and execute the program actually. So here, if you go to the run.sh, you have the entire script where the submission, everything is there. And if you go to the, let me just quickly go to the Makefile. The Makefile is basically I use the Spark-submit. That's what I use it actually. And then output directory, everything I mentioned. So with this, I'm able to get some results for the matrix into vector, which is basically useful in the many of our applications. I will now take another application which you get idea about I'm cleaning, make clean. It's cleaned everything. Now I go to the other one is PySpark examples. Database. What this database means here, there are two kind of database problems which are solving on Hadoop, MapReduce, and many companies, they have many database of the employees. The employees are basically a good example of this company database is Provident Fund. All the Provident Fund which they get the employees in many companies, they are stored in the Provident Fund office, and the Provident Fund office finally aggregate all the databases for an employee and get the result. The question comes, if employee works in one company, if employee works in another company, how do you merge the databases? And then how do we get the queries can be processed actually? In one company, the employee may have 10 attributes, other company have 20 attributes. How do you store this data and how do you process it actually? In the earlier generation, key value pair, RDBMS, normal key value pair will not work. We need some another kind of thing. That's what called NoSQL data pair. That's what NoSQL has been used in the Berkeley database, which we'll discuss also. So what you see in this program is basically employee data is a column names and a list of employees, and then department data and column names, list of department data, everything is there. And then we create data frames for the each employee data, employee column also. Then we able to join employee and department database, and how do we get the two databases can be integrated, and how do you process the employee, whether it's in the department from department 2. This is what the another application which is extensively used in all industries in the country. Huge amount of data you generate. That's why if you really see every month, last week of every month, a lot of processing is done for the salary part. And then many employees work in many companies, we need to integrate. This is a major problem. So to do this also, how the Hadoop Spark can be utilized, then how Berkeley DB can be utilized, that we'll discuss. So let us quickly see this one. Again, I usual make clean. Am I audible now? Hello?
So you are audible.
So what we do is that we again go to the readme file, and then we do the Spark submit, PySpark. So that means here 2-3 company employees databases can be integrated, and you can process the query also. Then let us see how it does actually. This also see. So here basically we are asking all this data. We need to go to the input file, output file, then we can see how the scheduler and how the yarn, everything really is giving all information. We need to study, analyze this entire output also that takes. But what we do, we have another program which is basically output, which is there. Let us see. More I do make clean. Clean is not there. It's make clean. So output report dot is also there. So now let us see. Now we run another program. Here we get the output also. We'll understand actually. Spark submit by Spark out. So I'm comparing another employee database where the output also generated. Let us see. I'm running now. Now it generates the output. So this is the output. So employee data set is given alpha, DID, age, salary, and then joint data set is given. Now we need to find the query. That's what the query is given comma. So that means large number of company databases which can be integrated and then process easily, especially for the financial aspects of Provident Fund, everything. So it is another program which we have done. One program we have done word count where the data size increased by 0.6 MB to 1.2 MB. Other one we have done matrix into vector where the program is very, very simple to write, where the matrix into vector is extensively used in almost all the applications in industry. And third one is the company databases where we can integrate. All these three are running on the high throughput computing system in the cloud. That means the cloud, earlier we discussed about this Slum scheduler and cyclic cloud running HPC applications. Now they are all integrated with the Yarn, and now under the Yarn, this Hadoop Python and Apache Hadoop Spark can run actually. So with this, I am completing some part of the Hadoop Python. Now I will quickly walk through the Berkeley DB and demonstrate some codes also. Let us see actually. Mute. Stop. Visible now? Audible?
Yes, sir. Visible and audible.
So now what we do, we talk about the databases, how do we manage on the cloud, what kind of program. One is use database is there, and then you require direct access to key and value pair. Now let us put other things which are there in the last 10 to 15 years. One is NoSQL databases. One is MongoDB is having NoSQL databases. MongoDB and writing a program integration is very, very difficult in the beginning, but now it's easy. Other one is Oracle purchased NoSQL database called Berkeley DB. Berkeley DB is a embedded database purchased by Oracle. Now it's called as Oracle NoSQL actually. Here, you write a normal program using like structures and indexes. And you ask the cloud to give me big storage of 1 petabyte or 2 petabyte, then I can able to run my program only. It's running a program, but not on the way you do the relational databases here. So there is a You don't require full functionality of the DBMS. You require only high performance. That means concurrently, can I able to access my data in the database or not? Yes, you can access. It only operates succession operation. Let us see. So now the Berkeley DB is part of the system. It's not in the storage. It's part of the system. That means I need a big system with a huge memory, more number of cores. Then I install the Berkeley DB. Then I directly use in my application. That means under the cloud, I need a big multi-core system, high throughput computing system, where I install Berkeley DB also. On the high throughput computing system, I have petabytes of storage. I have more number of cores. Then how do we process it? That means everything runs in a single address space. Single address space means I run my program on my laptop with Ubuntu OS in Berkeley DB. I run my program in big servers on the cloud with Berkeley DB. I can do everything together. That means the 95% of my time is invested in development on my laptop and hiring that system in the cloud. That's what the advantage. The application and database code run together. That means my application runs whenever I need a database command to be executed, I run one API, then automatically I get my answer. So this reduces the overhead of inter-process communication. So very, very low database operations are performed via direct function calls, not as a function calls, not like a DBMS, so low latency and high performance. So can handle database from few kilobytes to terabyte. Means TB of data I can handle using Berkeley DB, and it again uses key value store where data is stored and retrieved using a unique keys. Okay, because it's embedded in nature. Reading and writing speeds are much better compared to normal DBMS. Because reading and writing is performance better. Concurrently, you can read the data and you can process actually. So that means it's an application which where the program is running. Let us see the application also, you get idea. Data is stored in tables, conceptual schema. Data is actually organized in files and indices in physical schema. Whereas DBMS is a suitable storage structure. Here it is slightly different. So let us see all these things. Record number, the local record number is primary of the key nodes. Queues, the logical record number is the primary key of records. Data is stored in either fixed or variable length. It's embedded database. It uses hash-based approach for the random access. It keeps all the keys using B tree. That means many attributes, combination of many attributes to form a key for records, hash and B tree, which I'll tell you some examples which you'll understand. Now, what kind of programming APIs it uses is, one is open Berkeley DB, close a Berkeley DB, get items from get from BDB, put to BDB, return to BDB, and then declare the database secondary index. All these are APIs. Get put only extensively used, open close actually. So basically how to write in a typical C program, we write structures with different elements. That means you write a structure where the how you define the key as a key and value, and how to write the structure, normal structures we use. Let us see. So traditional databases that run on a separate server, Berkeley DB is designed to be embedded into the application. That means your one application runs, in that application you have Berkeley DB APIs, it runs very fast and you require everything actually. So now let us see, that means deploying is very easy and data operations are performed very easily. Concurrent access is there for all the things. Let us see. Now, in the case of telecom traffic, I define a structure which handles the cost, capacity, and traffic matrix. I define a structure for a commodity, that is inflow and outflow. I define a telecom cost flow, shortest path, maximum flow. That means my key is basically origin node, destination node, cost, capacity, and demand. My value is the shortest path from origin to destination. All these things I store it in my system with using embedded database using get and put, then I get the entire data for the one time interval. Then I go to the another time interval and store it. That means every day I keep gathering all the data and store it in Berkeley DB to get the complete data actually. Now, let us see some programs which we do also. That means we can able to do Berkeley DB multi-threading. We can able to do Berkeley DB using libraries. We can able to do Berkeley DB using message passing library. So all the things can be integrated. That is, Hadoop MapReduce is one side. Berkeley DB is one side. But if you want to run Berkeley DB on a cluster, 1,000, 10,000 nodes, then integrate with MPA. MPA and Berkeley DB, but not with Hadoop MapReduce in Berkeley DB. So that also we need to understand. We have some examples which we have done. Large scale matrices, a block matrix. A block matrix is a structure. Structure consists of number of rows of a block, number of columns of a block, and then values actually. Okay, value is the values. And we also do the large amount of graph coloring. How do you do the graph coloring? The graph coloring is extensively used in 5G telecom data, where the coloring sees that there is a 100 GB network is there between the high color and 10 GB for the next color and 5 GB for the next color. How do you process all this data? So this is how the large amount of graph data which is stored in the Neo4j, or we use Berkeley DB embedded database storage and process it actually. Now what we do, we'll give you some applications now, and with this we can close our today's session also. Let me just am I audible now?
Yes, sir, you are audible.
I close it now. I'll go to the my session now. I go to the system, logged out, 10.208. That is in 75. See that. Let me show the slide system for them. So I logged on to system now. That means I can run a large compute intensive, data intensive job using Hadoop MapReduce, Hadoop Python, Apache Hadoop Python, Apache Spark, where I can integrate GPUs and I can make it on the cloud. Another approach is I use message passing library MPI, which we discussed last time, and Berkeley DB integrated, then I can solve. This one is only one program you are running. So there is a lot of change in the way people are working on this actually. We'll share with you. Now, do you able to listen and what I'm doing, you are able to see also?
Yes, sir.
So now what we do, we logged on to the another system. See, there are two things we have to understand. Huge amount of data processing under the cloud. What programming paradigm do you use? Do you use GPUs? Do you use AI? Do you use machine learning? Based on that, am I using Hadoop Python? Am I using Apache Spark? Or am I using MPI? Or am I using PyTorch for the distributed? Am I using Berkeley DB for the concurrent large amount of data processing? And Berkeley DB integrated with MPI, PyTorch integrated with MPI. So almost all 95% of the programming patterns under the cloud, they are distributed in nature. That means we have to move on to the distributed training, distributed inference, distributed computing only. So let us see. I logged on to the system. Now I will show you how we do the Berkeley DB thing so that you get to understand. This, Berkeley DB. So I'm able to go to my directory PySpark. There is a BDB, there's a directory called BDB employee search is there. Okay, we got to the BDB. Are you able to see this program main.cpp? Are you able to see? Are you able to see this program?
Yes, sir. Yes, sir. We are able to.
So I increase the screen size. So now here I put the struct employee as a struct and I declare the age and department, salary and everything. So I have done everything about the structure and then attribute that the structure defined. These attributes of the structure vary from company to company. Even one employee works in one company, he may have 10 attributes. If he goes to other companies, salary, responsibility, job type, everything goes to the double actually. So now I go to the print database close store everything. Now let us see class database. That is DB, Berkeley DB environment, DB, M database, string database name. That is, I am now constituting the Berkeley DB environment actually. Database, cache size, M database, open the database and everything, DB exception, everything I am doing in the program. And then after doing everything program, I am closing the database. Database reading, database writing, which I will write another program also. Method to put employee in the database. If you want to put the employee in database, employee get. Employee get is the database actually, what we get employee. Then, and method to search the employee, bool search employee. So now you see database put means you are putting the employee information in the database. That is put this really see here this pointed to M database, that point to put entire key and value in the database. Put is a programming API is given actually. Above that you are written the value and key. What is the value? What is the key? Everything. Okay. Value is ID, key is ID, value is the size of the employee, all information about the employee. That means if VC raw is ID, VC raw 10 attributes, you can get it easily using this API. That's what the beauty of you see. Now you can see print employee and then the also employee print and all this. So now what we do here is that get also there here. While till whatever question you put, the question you say, get me information of the key and value in the database. That's what cursor pointed to get here. There you get cursor pointed to put actually. So get and put is one of the APIs which we use in the Berkeley DB. Then run the file. So what is basically here is that your employee put and employee put is there, and then database 2 and employee put. So all this thing is every employee information you put in the database. Now this one company database we can integrate. Earlier we talked about Spark Python. Now we talk about the Berkeley DB, that is no Oracle, no SQL. Oracle purchased the no SQL. No SQL is a Berkeley DB. Berkeley DB is open source available. Now we are using Berkeley DB. So now let's see. I am searching also. So the program is over. Now if you see the entire program, it is basically a 200 lines program where large company database, you are take the entire company data, maybe Excel sheet, then put into the Berkeley DB, then you ask many queries you can do. That means if you provide me Excel information about the all employees and every month, then I can able to dump it onto my Berkeley DB and I can process it actually. So now I will see to compile the program. Again, here is a make clean, make. Now you created the run is a binary ./run. When I compile, this is a CPP program, that is Berkeley DB. I integrated with the C++. Then I compiled, I created a binary called run, and I'm running the program. This whole program has run completely. You can see here the employee one, salary, name, age department, employee to age name department, and database to this thing. And then now searching employee for salary. You want to search an employee with the salary, that I can do searching. So what is the advantage is basically, similarly you want to search another employee with certain salary, it's a record not found. That means you can integrate 100, 200 a company databases together, and you can use the Oracle NoSQL. That is what the Berkeley DB is, a programming APIs. Let us again go through this programming main.cpp. This is how the program written here. That means my key value pair is stored in the structure and in the indexes, that is structure and attributes. Once it's stored in structure and indices, I push my data into the Berkeley DB using BDB put, and once I want to get the data, I use BDB get actually. And I am also opening Berkeley DB, and I am also closing the Berkeley DB also there. Opening, that is reading, writing, get and put, all things happens in this. Now let us run another program, and after this we'll try to consolidate. Again I say make clean, I clean. Now I have another program called BDB CD, BDB read write. So what I'm doing here, last 7-8 days, people talk about the entire cloud infrastructure, resources, programming. Today we are running programs where the large databases of terabytes can be integrated using this programming language, and then we can run on the cloud also. So now we'll see, I'm also giving another example of read write, more read write. So it's a reading how to open a Berkeley DB, open DB open Berkeley DB, and then key and data. Put the data in the, once you open the file, put the data. And if you want to retrieve, then again you get the get data, get cursor pointed to get, you get the data. Here put the data actually. So put the data, get the data, all these things are basically used in the Berkeley DB. Now close the data, the program is over here. That means now that means traditional DBMS, Berkeley DB is totally different. Berkeley DB you can handle terabytes of data, simple programs only. And these programs have a concurrent read thing, so very, very advantage. Now let us see again. I'll do the more make file. The make file is there. In the make file, I'm using read write .cc and everything, and then say make. I completed the make file. I created the binary file run. This is a 64-bit binary is created. Then we run the /run. The DB exception, some input is missing in this. Let us see another program which we run. BDB. Let me go to the BDB read write. Make clean. It's clean. We need to see why exception fail is there. We run other one, BDB array sum. Here make clean again. So what is important? That the DB a folder is there in the directory, because DB folder is there, which without that we cannot run. So I just say make. I'm running large array of sum of all the values. Then I'm getting sum of array is 15 elements. Let us see the array sum. Array sum.c. This is how the program written. Again DB put key value pair. You define a key value pair. In case of matrix into matrix multiplication, you define key value is one row of matrix, one column of matrix, value is the dot product of two vectors. Or you define key is the one value of matrix A, one value of matrix B, multiply, you get the value. Similarly, in the case of telecom traffic, origin node, destination node, cost, capacity, demand, that's the key. Value is the shortest path. That's how we define and solve the large problems. This is how the addition of integers. Another problem I will solve you, and then I will run this readme file also, and then close it now today. Read write. So read write, why we are not able to done read write properly is we do not have the DB file. That's why it's having some difficulty. Let's put the DB file, CP minus DB here I put. So I put the DB file also. So make no dot slash run. So it has run now. That means basically reading a file, writing, all the reading, writing, pushing data into Berkeley DB, getting data from Berkeley DB. All these things you're writing in standard programming APIs. So with this, what we discussed today is large amount of data. Either you process the large amount of data using one programming pattern called Apache Hadoop Python. Second one is we also integrated with Apache Spark. And third one is Berkeley DB. All Berkeley DB the NoSQL. SQL DBMS, Apache Python key value pair, Apache Hadoop Python key value pair, Apache Spark Python key value, traditional programs and DB key value, all things we have given the demonstration, we have gone over you also. With the Berkeley DB, that is Oracle NoSQL, Oracle Berkeley DB they call, you can solve large data intensive applications. Your responsibility is to define key value pair as a structure, and then standard program, if you write it with Berkeley DB, get and put and read and write APIs, then you can demand what resources do you require on the cloud. Once you know the resources, then you can run. In the case of Spark, you require a system with use in memory with the storage compatibility, then you can run Spark Python. Whereas in the Hadoop Python, you require, if the problem requires more memory, if it doesn't fit into the memory space of the system, it writes to the storage. So all three we checked today. We have done a kind of demonstration of all these three. And I'm about to close. Any questions are there, Adam? Very good, the questions here.
Sir, your mic is on mute if you are saying.
Any questions are there?
Participants, if you are having any queries, you can put up in chat box.
Thank you very much.
So, sir, I think there are no more queries. So, thank you once again, sir, for contributing to our FDP program, and it was like very insightful for getting information from you. Thank you so much, sir, once again.
I will definitely send my PDFs of the presentation maybe today or tomorrow.
Okay, thank you, sir.
Tomorrow morning, and then thank you very much. Okay. Okay. Shall I close now?
Yes, sir. Yes, sir. To the participants, we will be meeting again tomorrow at 9:30 a.m.